set Søren komme. Det ved du, om han kommer.
Har du hørt fra ham? Ja. Jeg må ikke komme ud i byen, hvor jeg lige snakkede med.
Jeg havde meget svært ved at få kontakt med ham, faktisk. Jeg har prøvet flere gange, men jeg ved ikke, om det har været... Det kan være, det har været lidt for tæt på og lidt for hårdt.
Det gør det.
Det er så sjovt. Og man skulle have haft nogle udfordringer.
Ja, det må man sige.
Og det gør ikke.
Ja.
Men lyd, men de har vel også nok til med de der nye fly, der kommer. Der skal sikkert laves en masse målinger og vurderinger af både den ene og den anden slags. De skulle larme noget på den.
Ja.
Good afternoon, and welcome to this defense of a doctoral dissertation by Professor Mads Græsbøll Christensen. My name is Henrik Petersen, and I'm the Dean of the Technical Faculty of IT and Design. And I will act as the moderator for this defense. On behalf of the faculty, I would like to welcome you all. Mads Græsbøll has submitted a doctoral dissertation in order to obtain the title of dr.techn, dr.techn. And the doctoral dissertation is entitled Model-Based Analysis and Processing of Speech and Audio Signals. And is based on a survey, again based on Mads Græsbøll Christensen's papers. The Academic Council has appointed an assessment committee to assess the doctoral dissertation by Mads. The committee consists of 3 members, 2 external opponents and 1 internal to Aalborg University. The internal member has acted as the chairman of the committee. Chairperson, maybe. The committee consists of the following members: Professor Stefania Serafin, Chairman, and Professor Gail Richard from French Telecom in Paris and the Institut Polytechnique de Paris, 19, and Patrick A. Naylor from Imperial College London, Department of Electrical and Electronic Engineering. The faculty would like to acknowledge the committee for the substantial effort invested in evaluating this dissertation. Now the program for today is divided into 2 sessions. First, Mads Græsbøll will present his work for a maximum of 30 minutes. After this, we will have a short break, around 15 minutes, and then we will begin the session with questions and discussions with the assessment committee, followed by questions ex auditoria. The session will last no longer than 3 hours, not necessarily for 3 hours, but no longer than 3 hours. And is followed by a reception just outside this seminar room in the AAU canteen. So now we know the program, and I would like to invite Mads Græsbøll to present his work. Please, Mads. go. This thing managed to turn itself off in the meantime. It worked just fine a second ago. See? There we go. Welcome everybody, and thank you for coming here today and attending my defense. I'll be giving this talk here, which is entitled Model-Based Analysis and Processing of Speech and Audio Signals. And what I'll be talking about here today is what you might call a bit of a retrospective work, looking back at many years of doing research. And looking back, there are certain ideas that sort of permeate my research over the past few decades. And briefly put, my research has revolved around the ideas of describing and analyzing audio signals using models, namely parametric and statistical models, and then posing, analyzing, and solving engineering problems in speech and audio using typically methodologies such as optimization, linear algebra, statistics, and so forth. And what I'd like to do here today is tell you a bit more about this model-based approach that we have to our work and what can be achieved with it. And I can't be exhaustive here in my 30 minutes, so what I'm going to do instead is that I'll be discussing a specific model and using that for discussing this model-based approach. So here's a brief outline of today's talk. I'll start out explaining a bit about the model-based approach, then a bit about a specific model, namely the harmonic model, then a bit about how to estimate the nonlinear parameters of that model, more specifically the fundamental frequency, and then I'll talk a bit about some other topics, namely pre-widening, separation and noise reduction. I'll talk a bit about how to deal with non-stationarity and how to apply these ideas in array processing, and finally I'll go over the contributions and conclusions of the thesis. All right. So my research has basically aimed at answering the questions of what are good models of speech and audio signals recorded in adverse conditions, and how do we find their parameters, and how can we use them. And as you can see in this picture, if you have, for example, a meeting with several people talking at the same time, conditions are actually quite poor. If you try to record it, because there might be people talking at the same time, there might be background noise, there might be reverberation, and also the equipment might actually distort the recordings. So the whole question is, how do we model the speech signals, and how do we estimate the parameters of the signals, and what can we do about the noise and so forth. So what is this model-based approach about? Well, it's basically processing based on what you might call generative signal models that have parameters that are physically meaningful. Such models are not new, and this is not a new idea. In fact, some of the criticism we sometimes hear is that we tried it in the 70s and it didn't work. And again, people tell us that our models are wrong, and even if they were right and were useful, it would be possible to estimate the parameters. And hopefully today I'll convince you that this is not the case, because we firmly believe that these models can be used for many things and in many different ways, actually also. And key point is that this approach here leads to robust, tractable, and often also fast methods that can be analyzed and improved if there are any problems. And also, I think in this day and age, with all the deep learning and data-driven methods, I think we should all remember also that the models are extremely important, and even if they're not explicit, there are models in everything we do. And there's this nice quote by Rosenbluth and Wiener from 1945, which says that partial models, imperfect as they may be, are the only means developed by science for understanding the universe. Good. So what's a good model? Well, it's certainly one that fits our data well, in my case, speech and audio signals. I would also argue it should be physically meaningful. And finally, it should be as simple as possible. And there are many technical reasons for this. And what I'll do now is I'll explore this model-based approach with an example showing how we can model speech and audio signals, how we can estimate parameters, and how we can use and improve the model if need be. So here's an example of a speech signal, more specifically a spectrogram showing the distribution of the power over time and frequency. And this is what we call voice speech, and this is utterance Y where you weigh your Roy. This is a bit of a special case because it's all voiced, but that's the the context that I'll be talking about today. But we can see a number of things here that are interesting. Firstly, the spectra is highly structured. There's a distinct pattern to the signal, and we can see also that it is non-stationary, meaning that it evolves all the time. So actually, you can also imagine that this would actually be somewhat of a difficult task to model. And then, of course, also in practice, if you go out and try to record this, there's going to be signal degradation, such as noise and background noise. So a model that we looked at a lot, which is well suited for those kinds of signals, is what we call the harmonic model. And this model is aimed at periodic or approximately periodic signals, which are sort of the cornerstone of speech and audio signals. And the model looks like this. We have a signal x of n that is recorded, which comprises a signal interest S of n and some noise E of n. And then this S of n is modeled as a sum of complex exponential functions, complex sinusoids, whatever you want to call them. And the special thing about this model is that the frequencies of these complex exponential functions are integral multiples of a fundamental frequency, omega 0. And we have, as you can see here, an index L, which indicates a number of harmonics. So the individual components here are called harmonics. So we have this S of n, which you can think of as being a deterministic component. And we have this E of n, which is the noise, which is stochastic, and may actually also capture other kinds of stochastic components. And then each of these harmonics has a complex amplitude comprising a real amplitude and a phase. We can write this model in a number of different ways that are useful in matrix vector notation, as you can see here. So we make this vector x of n, in which we collect m samples of the signal there, and then we can define matrix sets of n comprising the individual harmonics in its columns. And the model can be written in a number of different ways, which are useful in different contexts depending on how we would like to look at the time dependency here. So we can also rewrite this with this E of n matrix with diagonal matrix, which translate the signal to explain time dependence. In understanding these signals, we can also look at the covariance matrix of x of n. And it can be shown then that this can actually be expressed in terms of this model here. So in equation 6, what you see is that the covariance matrix R can be written as in terms of the set matrix and times a P matrix and set Hermitian transpose plus a Q matrix, which is the covariance matrix of the noise. And then this P matrix, you can show under a number of different conditions that this tends to a diagonal matrix containing the power of the individual components. And then often in applying methods, people assume that the background noise, the Q term here, the covariance matrix of it, is a diagonal scale diagonal matrix, even though this is very often not the case, but we will return to that later. Now, often in signal processing, you apply filters to signals. So what happens if we apply a filter to this signal X? So we have filter coefficients H. We apply this as an inner product between H and X to get an output Y. And if we express then the signal in terms of the model, we can see that in equation 8, that both the periodic signal described by the set matrix and the noise will be affected by this filter. We can also express the output power of the filter, which will be useful later, in terms of these quantities here, as we see here in equation 9. And again, we can see that there's a term that has to do with the signal interest, the S part, the periodic part, and then also the noise part. Another useful tool that we have for analyzing such signals is the eigenvalue decomposition, which can be used for finding some useful properties of the signals. So the covariance matrix R can be written in terms of the eigenvectors in the orthonormal eigenvectors in the U matrix, and then we have a lambda matrix diagonal, which contains the sorted eigenvalues starting with the largest one. And then we can partition these eigenvectors into two matrices. We can define an S matrix containing the first L ones corresponding to the largest eigenvalues. We can take the last ones, put them in this G matrix, and then we can show that that the set matrix for the true fundamental frequency should be orthogonal to this G. And secondly, that the range, the column space of S should be equal to the column space of Z. So we can ask a bunch of questions about this model here. So firstly, it contains nonlinear parameters. Can we estimate those? Because that might be very difficult. Secondly, can we take non-stationary into account? So can we take into account that these signals change continuously? Can we deal with interference and noise? And can we extend the model to arrays, meaning that we don't have one channel, we may have many channels. So let's find out. So to understand the fundamental frequency estimation problem and what can and can't be done, it is useful to study the Canary lower bound of that problem. And what's the Canary lower bound? Well, it's a lower bound on the variance of an unbiased estimate of a quantity, say the fundamental frequency, and it can then be shown that the variance of that quantity is larger or equal to the inverse of the Fish information matrix, the energy covariance pointing to it in that matrix. Where this Fish information matrix is the second order derivative of the expected value of the second order derivative of the log likelihood function. Now, the interesting thing here is that if you work this out for the model we just looked at under the assumptions that were mentioned, then asymptotically the variance of the fundamental frequency is given by this expression you see here in equation 15. And we can see, well, it depends on the noise variance sigma squared. That's to be expected, of course. We can also see that it's inversely proportional to NQ, which tells us that the more samples we have, of course, the better an estimate we're going to get. And then it depends on the complex, the real amplitudes AL squared. So essentially, in that sense, the power of the signal here. Now, how is this useful? Well, we can try to take a look at what this looks like for a number of different cases. Say we assume that we have a certain number of harmonics. We can say we can have 5 and we have 10, and we have amplitudes, and they're all the same amplitude, it's just one, and there's a certain noise variance. Then we get the yellow and the purple lines here, which tells us we can estimate the fundamental frequency equally well for all possible fundamental frequencies. But then if we recognize that the number of harmonics we may have in a signal depends on what the fundamental frequency is, because the harmonics can go all the way up to half the sampling frequency, then we actually get a dependency on the fundamental frequency. And this is exemplified here for 2 cases in the red and the blue lines here, showing the case for unit amplitudes and for decaying amplitudes. And you can actually see that there's something that akin to a linear relationship between the fundamental frequency and the parallel bound for those cases on these logarithmic scales here, which is, I think, very interesting. So it is, in fact, possible to estimate lower fundamental frequencies more accurately than higher fundamental frequencies when you look at this way. So it's an example of how you can use these tools to actually understand the problems we're trying to solve better. So what about actually estimating the fundamental frequency? Well, if we assume white Gaussian noise, so this Q matrix is equal to a scaled energy matrix here, then we can express the likelihood function as seen here in equation 16, and then the maximum likelihood estimator can be derived as you see in equation 17. This is done by Barry Quinn in 1991. And this essentially boils down to, in this case, just changing the fundamental frequency of your model until you capture the most energy of the signal. And then if you use that complex exponential functions are approximately orthogonal, if you have long enough segments, large enough n, then you can actually rewrite this into what you see here in 18. And what you see inside the absolute value there is something that can be recognized as just the Fourier transform of x of n. So it means what we must do is simply add up the power where we may have the harmonics in the signal to find the fundamental frequency. And this is one of the oldest known fundamental frequency estimators that dates back to 1969. Peter Knoll introduced it. Interesting, in recent years, we managed to show actually also that the equation 17, you don't need to make the approximation there. It is in fact possible to solve it fast, meaning that you can actually have an optimal estimator that's even suitable for real-time applications. All right, there are other ways we can estimate the fundamental frequency that we have looked at. One is using some of these subspace properties I mentioned before. So we saw that the matrix set should be orthogonal to this G matrix. The question then begs itself, of course, then when you have actual signals which are noisy and so forth, how do you measure that something is orthogonal in a multidimensional space? And this is not a trivial question at all. But one way is using what is known as principal angles, which are defined as what you see here in 19, involving the projection matrices for the set matrix and this G matrix here. And actually these kappas that are defined here are actually just the singular values of the product of the two projection matrices here. But then what we showed is that you can estimate the fundamental frequency and actually also the number of harmonics, because these relationships only hold when you choose also the correct number of harmonics here using this idea here. And you can express this using the trace of the product of the two projection matrices, or you can make an approximation that can be implemented with FFTs as you see here in 21. So you can actually do this using suspect methods. What about filtering methods then? We saw earlier that the filtered signal could be expressed using the signal model, the harmonic model. And then we might have the idea then that what if we actually design a filter that passes the harmonics of our signal undistorted, but attenuates everything else as much as possible. And we can pose this as a constraint, gradient constraint problem with linear constraints in question 23. And you can show that this has the solution that you see in 24, which is a well-known solution in many different kinds of problems. But then what we showed is that you can estimate the fundamental frequency by applying then this filter to the signal, and you end up with the expression that we see here in 26. So how do we deal with colored noise? As we saw, many estimators, including the fast maximum likelihood method, assumes that the noise is right. So how do we deal with that? Well, if the noise term E has covariance matrix Q, we can select a transformation x of n that we call A here and apply that. And then if this A is selected as the Cholesky factor of the inverse of the covariance matrix, well then actually the resulting noise term will just be white and have variance 1. And you can actually implement this with filtering, so you can do this quite easily. The hard part actually is estimating the noise covariance matrix, because noise tends to be very non-stationary for speech and audio signals. But fortunately, there are a number of different approaches to this. For example, the noise trackers that have been developed for speech enhancement over the past few decades, parametric non-reaction matrix factorization methods, and also you can use the harmonic model in various ways to estimate the Q matrix actually. So there is a number of ways of dealing with that. What about if we have multiple sources, and what about dealing with noise? If what you're actually interested in is the output of the or one of the sources. So we can write then the signal as a sum of k sources, and of course sources here are indexed by k. And then we can see that now it looks very complicated. We have a bunch of periodic signals, and we have some noise. But we can of course separate that such that we have one of them is the target, and then we put everything else in the other term. It's a bit more complicated than that, of course, because some of the components may overlap and so forth. But in principle, we can look at it this way. But then the noise is no longer Gaussian, and then if we take a look at the filtered signal x of n, and again looking at it, what happens if we apply the filter to the model, we can see that again there's two terms. There's a term that has to do with the signal of interest, the periodic signal, and then the interference and the noise. We want to get rid of the interference and the noise, but we want to retain the periodic signal actually. And we can see that if we impose this constraint here, that the filter emission transpose times the set vector gives you one vector, then actually the output of that term is just going to be a sum of the harmonics. So exactly what we want. And again, we can express the output power of the filter in terms of the covariance matrix model. But what we notice now, unlike when we're looking at fundamental frequency from before, is that what we want actually is to minimize the output of the filter when applied to the noise, but subject to the constraint that it doesn't touch the noise and interference rather. But it doesn't touch the periodic signal we're interested in. Again, it has this well-known solution that you see in 32. This filter here is what you might call a comb filter, and it's adaptive and it's optimal. Comb filters have a rich history in signal processing, and specifically in speech and audio processing. And you can then also see that from this expression here in 32, first of all, you can actually get the solution from before if you just use R instead of Q. That's fairly obvious. But if you then use Q being equal to a scale density matrix, then you can see that you're actually getting something involving the pseudo-inverse of this set here. So something quite closely related actually to to projection. That's one thing. But secondly, also to this maximum likelihood estimated we looked at earlier. And finally, if you use again that the complex exponential functions are asymptotic or orthogonal, you actually end up just with filters which are basically normal Fourier bases. So this filter design here reduces to what you might call very intuitive and simple cases when you use those policies. Yes. So what about non-stationarity? Can we deal with, for example, a time-varying fundamental frequency? And you might also ask, if so, does it matter? But to explore this, what we looked at was a more general signal model, the one you see here in equation 33, where we have a more complicated function in the exponent of the complex exponential function. We now have this theta L of n, which is what you call the instantaneous phase, and a time-varying fundamental frequency function, omega 0 of t. Then if we assume that omega t is slowly varying and model it as a linear function, we get that this instantaneous phase function is a second-order polynomial function having both a fundamental frequency and a phase. We had that before, but now it also has a fundamental chirp rate. And this model is what we call the harmonic chirp model, and we have found ways of estimating both the alpha 0 and the omega 0 here with these non-least squares methods here. And then interesting, also, it is possible actually to compute optimal filters also for these non-stationary signals, which was, well, I could say for me at least, it was a bit of a surprise that that's even possible. Yes, and if you take a look at the spectrum of the two models, the harmonic model, the green one here, you see that it has a very regular and nice shape throughout the spectrum. But if you look then at this chirp model here, what you see is that because of the modulation by the chirp model, then the higher harmonics are more and more modulated, they're more and more distorted. And for us, actually, this answered some questions about why, for example, the model selection, the order selection, the harmonics often fails for real signals, and why it is so difficult to capture the higher frequencies of speech signals and so forth. So you can see this model really explains this well. So what about rate processing? What about if we have multiple channels? Because, of course, sensors are available now, MEMS microphones and so forth, so we can put sensors everywhere. Well, just to exemplify how these methods and ideas can be used in arrays, we can take a look at a simple case where we have a uniform linear array. So we have a number of microphones here with these small circles at the bottom. They're d meters apart. And then we have a source, which, where we here assume that this is what we call the far field and the planar waves. And then the idea is that we can estimate the phi, the angle, by looking at the time differences between when the signals arrive at the different microphones. And because it's a linear array, there's a distinct pattern to when this will happen, which is given by this expression delta k here, which relates the delay between the signals arriving at different microphones and the angle. So then we have that the signal of interest, which was S, we're going to have different S arriving at different times for different microphones, and the microphones are here, indicated by k. So we have an sk of n, which is equal to the signal of interest, S n minus delta k. So we end up with a model here for the cave channel that you see here in 35, where then we can explain, as you can see in 36, the delay between the different channels in a fairly simple way. So this shows nicely how an array geometry can be incorporated into the model in a simple way. And there are many other problems that you have in array processing, for example, dealing with fractional arrays and stuff like that, that are actually really simple to deal with in this model. So if we take the observed signal here and organize it in a matrix here, so that we have each column, we have a time instance n, we have the signals received by the different microphones, and then we can see that from this data matrix here, X, we can actually get the usual model by just applying this IK vector, which is the kth column of I. So we get the usual model there, and we have the delay delta k explaining how this relates to the signal of interest. Then we can define spatial frequency, this omega s, as you see here, and then a couple of vectors that are really useful. The details here are not that important, but I'll just go over it and then make my point. And then introducing this gamma quantity here,
we can write the data matrix as you see here in 41. And then we can actually write this in a very convenient way and using the tools already at our disposal by vectorizing these quantities here with the vec operator here, as you see. And then actually here at the bottom you can see that this set bar model here, which is a vectorized autoproduct of these set S and set T here, you can write this conveniently using the Kronecker product. And this enables us to design filters here for extracting periodic signals in time and in space simultaneously by putting all the vectorized harmonics into this set bar matrix here, and then we can design optimal filters that minimizes the influence of interference and noise while preserving the periodic signals. And we can compute the optimal filters just as we did before for as you see here in equation 46. And finally, we can now find not just the fundamental frequency, but also the angle from which the source is impinging on our array. So we can jointly estimate fundamental frequency and angle in space, which enable us to track better multiple sources and so forth as they may move around. And the same filters can also be used for separation and noise reduction, as we've already seen for the simple case. All right, so the key contributions of the thesis, and I said I could really be exhaustive here in my presentation today. So more specifically, in the thesis, there's new methods for order estimation in paper A. There's optimal filters for periodic signals, papers B and E. There's fundamental frequency estimators, paper C. There's model estimation filters for non-stationary signals, papers D and E. And there's something I didn't talk about at all, which is sparse linear prediction, paper F, which I also would say is one of my main contributions in my career. And then finally, this model-based array processing, which is paper G. I would like to mention a few other contributions that are closely related to what I talked about here, but it was not included in the thesis. So, for example, this result that the NLS, or maximum likelihood estimator for the fundamental frequency, can be implemented fast. That's one important result, takes it from being impractical to being practical for real-time use. And secondly, also that you can incorporate this in a fully Bayesian framework where you do tracking over time and all these kinds of things. Another thing is that soft-based and optimal filtering methods specifically for enhancement and separation and beamforming, those kind of problems, you can actually unify that in one framework. They were previously considered separate kind of methodologies. We've also shown that model-based enhancement can improve speech usability, even the very difficult case of babble noise. And when I say improve speech usability, what I mean is that this has been shown in actual listening tests, not just with simple objective metrics. A curious thing also, showing what you can actually do with these model-based approaches, is that if you model all the details, which we did for electric guitar, you can actually detect which string you're recording, what the fret is, what the picking position is, and all kinds of funny things, which really show that what you can do with these models in specific instances. Parametric NMF can be used for estimating statistics for pre-writing. It's an important thing. And finally, also this model selection problem. Finding the number of harmonics, not only that, but also choosing between different models is a problem you see again and again in science and engineering, and we've made a number of contributions to that. And actually, I also like to remark that that problem actually often pops up in places where you don't notice it, and you just notice funny behavior in methods, and then only many years later do you realize that this was actually because you were comparing apples and oranges. Finally, regarding this sparse linear prediction, I would also like to add that we have developed real-time and stable sparse linear prediction methods, which are actually important steps in making those things practical. So, those of you who are not so mathematically inclined are probably wondering, what's this all good for? Well, you can use these things in hearing aids where you can extract sources that simulate noise and stuff like that. You can use it for voice analysis, for example, analyzing voice and diagnosing illnesses. You can use it in telecommunications for, again, removing noise and interference, of course, but also for solving other problems such as feedback and echo cancellation and things like that. You can use it in reproduction systems. You can find faults in rotating machinery and pumps and stuff like that. And you can, of course, also use these things in music equipment because It's very intimately related to the models I've talked about. So final conclusions here. As we've seen, there's a number of advantages to the model-based approach. Critical assumptions can easily be identified and be mitigated. I think we've seen that again and again. And the harmonic model is very useful for modeling approximately periodic signals such as those found in speech and audio. And it's possible to estimate the parameters in quite adverse conditions, actually. And we've also seen that computationally efficient methods actually do exist. It's possible to deal with noise, interference, and non-stationarity, and we've also seen it's possible to extend the principles to arrays. And I would also say that I think personally that there are many more problems that could benefit from this approach here. And particularly, I would say multiple channels, wireless acoustic sensor network and stuff like that, where you can't use the geometry and all those things that you relied on in the past. But also where the fine details and the conditions are adverse, and where the physics, the underlying physics really matter. Such as, for example, is the case if you're trying to understand the effect of illnesses on the voice, for example, how Parkinson's might affect the voice. Yes. Well, that's it. There are a number of people who deserve to be thanked, of course, and current former students, of course, and collaborators. Some of you are here. Thanks so much. And Jesper, I think, deserve special thanks for all our work over the years. There's the one Jesper. What's the other Jesper? Oh, there's the other Jesper. Thank you, guys. Family and friends, thanks for coming here today. And my son, Eric, where is he? Oh, let's see. Oh, there you are. Okay, there's stepping on that there. I saw you, it's up there. And then finally, this lovely young woman here. Thanks so much.
Thank you very much, Mads, for this very interesting presentation and spot on in time and everything. So now we'll have a little break. Let's agree that we adjourn at 12:45. Okay?